Let's discuss the linked data question 52 and 53. Okay, so a combination of spring and a damper is given. So let me draw the figure. K1 C, mass M. Okay, and you have a spring, another spring K2, which is connected to an attachment, and this attachment has the motion xp. So attachment B is given a motion of this form, xb as b cos omega t. Okay, so this just to mention, this question is from Theory of Machines, test 3. Okay, so let's continue with the discussion. Okay, so attachment B is given a motion b cos omega t, and the first bit we are supposed to find out the equation of motion for the mass m. So the equation of motion for the mass m, the only way is to let us draw the free body diagram of mass m. The free body diagram of mass m when it is displaced by amount x. So when the mass m is displaced by amount x, so this spring, this damper will oppose the velocity. So at time t, the mass has displaced by amount x and the velocity is x dot. So then the damper exerts a force ch dot opposite to the velocity direction, and the spring K1 will oppose will exert a force Kx in the opposite direction. So this is K1x because there is a spring is K1. Okay, now spring K2, let's come back to spring K2. Now spring K2 is stretched by xb at point B and near the mass, because the mass is displaced by amount x. So assuming that x is greater than b, let's take, this is, you can take the other way also. You can assume xb is greater than x, you will end up getting the same answer. So let's take x greater than xb. So the spring K2 is basically compressed. So when it's compressed, the spring will try to expand. The spring will try to expand and so exert a force on m in this direction, and the value is K2 into the compression of the spring, which is x minus xp. Okay, so these are the three forces on the spring, and so with the effect of these three forces, the mass, so this is my free body diagram, so the mass will have an acceleration mx, the inertial force mx double dot. So equating all the terms on the free body diagram to the terms in the inertial diagram, this is my inertial diagram where I have represented only the inertial forces. Okay, so let me just use the equation of motion where all the forces in x direction, this is my x direction, are represented. Okay, so I represented positive. So now minus K1x is on the left side, so I'm writing like this: minus ch dot minus K2 x minus xb is equal to mx double dot. Okay, so now when I just rearrange the terms, so I end up getting mx double dot plus K1x plus K2x plus ch dot and K2xb. Let us keep on the right side. So I can just K2xb, I just return as like this. So mx double dot plus K1 plus K2 into x plus ch dot is equal to K2xb, or just to put in the standard form, so K1 plus K2x is equal to K2xb. So this is my equation of motion. So the option for this is B. Okay, so now because it's a linked question, so let's discuss 53 also. So in 53, what is asked is the critical frequency omega c at which the oscillations are large. Okay, so now if you consider a single mass system, a spring and a damper system, the equation of motion is mx double dot plus k Ch dot plus Kx is equal to 0. So in this case we know that the critical frequency at which the amplitudes are large, or in fact the amplitudes are large in the sense the resonance occur is at a frequency when your omega c becomes, omega c is again your, suppose you are imparting a forced vibration, so then this omega c, if it equals to the natural frequency of the system, which is k by m in this case, then the amplitudes are large and this state is called resonance. Okay, so now let's compare this equation with this equation, and then omega c is basically your k by m, and what lies in the k term is k1 plus k2, and so basically you are comparing this equation with this equation. So your k1 plus k2 by m is your critical frequency at which resonance occur. So I mean, because this value is your natural frequency of this system, so this you get when you compare this with the left side of this is compared with the left side of this, and so the natural frequency in this case comes out to be k1 plus k2 by m, and that is your omega c for high or exceedingly high amplitudes. So the answer is A. The option is A. Thank you.